Okay, let's get started. So 4 people are on Zoom. Some will be joining probably. So today we are going to basically look at our model system where we have n particles that are distinguishable and independent of each other, and solve it through 3 different ways. We will try to set it up through NVE, which is microcanonical, which we did last time. So we'll continue that, canonical, NVT. And then we will look at a third, much simpler approach and see how that works. And after that, we will start with the grand canonical ensemble, where the number can also fluctuate. The grand canonical ensemble will not be on midterm, which is next week. So the next week, the midterm, the way it will work is it will be released online Thursday morning, early morning. And what date is Thursday? 30th. February does not have 30th. So what date is it?
March 2nd.
2nd, right? I take your word. 2nd March. And it will be due. When should I make it due? What do you think, Arun? We go by you. You tell us. Friday morning?
Oh, yeah, of course. I don't know, maybe a week.
Tuesday morning in class. How about that? Okay. Now you're just going to have a sucky weekend. I mean, hopefully not. I didn't say anything like that.
Do you still have class that Thursday?
No. No class. So at least you have class time to start thinking about it. That's the idea. And it's open book, open chat GPT, which sucks for StatMech, as we saw. The answer it gave Alex was really wrong. It looks intelligent. I posted it on social media and people responded, oh yeah, that looks right. And then people are trying to delete their comment because they realize it's actually completely wrong. It's like a very convoluted answer, which has, yeah, anyway. So you can use whatever you want. You cannot just talk to each other. It's your work. Okay. So no discussions, and it's an honor code in that sense. And it will cover microcanonical and canonical ensemble, not the grand canonical ensemble. Okay, so let's, and any questions about that? Okay, so let's get started. So we were talking about n particles, which were distinguishable, which were independent. So they did not really know what was going on with any other particle. And they could exist in one of 2 energy states. For those who are coming late, you should make sure to watch the video and check up on whatever I said about the exam. I'm not going to repeat it. One of 2 energy states. The ground state is energy 0. This is per particle. And an excited state is energy epsilon. E is equal to epsilon, okay? So we can draw some sort of a box like this, where this corresponds to different particles, and we can label it this way because the particles are distinguishable. If they did not have distinct identities, then I could not say this is particle 1, this is particle 2. And if the particle is here, that means its energy is epsilon. And if the particle is down, that means its energy is 0, something like that. So we can fill things like this. So the microstate of the system, nu, can be written as a long binary number, a n-digit binary number, which looks like, for example, for the one that I drew above, it will look like 1, 0, ... and the last one will be 1. Right? We don't know anything about the ones in the middle because we did not write it down. So, and this is a complete microstate for this system. So intuitively, it makes sense. Through intuition, it makes sense that the energy of the system, of the full system, all particles, at ground state is going to be 0, at t is equal to 0. Because everything goes into the ground state. One of you asked about the excited state. It was not clear. I mean, at high temperatures, that T tends to infinity. At As t tends to infinity, basically what this means is that the value of kT is so much more than epsilon that whether you are in zero, whether you are in epsilon, that means nothing. That's pure noise. Okay, that's the idea. So it's like you're observing something from outer space and you're saying whether you're on ground floor or on first floor, right? That's well within your error margin. You cannot really resolve even that, right? It's just thermal fluctuation. That's if your energy level corresponds to you moving from here to moon and back to moon, then are you really going to talk about ground floor and first floor? Now, it does not make any sense, right? So you could be with basically the same probability in the ground state or in the excited state, which means every particle can either be in zero or in epsilon. So the average energy is going to be epsilon by 2. That's where we get from. This is intuition. Now what we want to do is to prove this rigorously through microcanonical and through canonical ensemble. So we are going to do 3 approaches. The approach 1 is NVE ensemble. So in this, we set it up last time, and we really don't have any volume here. So we are talking about omega as a function of NE, the number of microstates the system can have. And in order to do this, we set up that if the energy of the system is given by m multiplied by epsilon, where 0 less than equal to m less than equal to n, right? The total energy of the system has to be between 0. You don't have negative energy. It cannot go lower than 0. Or everything is in the top state. If everything is in the top state, then the total energy is equal to n epsilon, right? That's where this range comes from. So m can take value between 0 and capital N. So we said this is the number of ways of arranging ones in between this binary number, right? So if you have, for example, if n is equal to 8 and E is equal to 4 epsilon, then the microstates that correspond to this configuration would look like 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, right? While this one is not a consistent microstate, right? Because it has 5 states. The energy of this one is 5 epsilon. So this is not allowed. So we have to count the number of ways we can put in, the number of ways of picking m things out of n. And that is capital N choose m, or n factorial by m factorial by n minus m factorial. This is what we showed last time. Okay. So I'll write down this expression on the next page. I'm just recapping so far. So omega of NE is equal to n factorial by m factorial by n minus m factorial. And here what gets confusing is what is small m? So E is equal to m epsilon. In other words, m is equal to E by epsilon. So this is equation number 1. We have counted the number of microstates, but that's just StatMech lingo. We haven't yet made our way into thermodynamics. So now what we have to do is to go from here to thermodynamics. It's a microcanonical ensemble. Anytime you have a microcanonical ensemble, what is its... So those who are coming late, please make sure to watch the video to see what I said about the exam, okay? Or it will be a total surprise and you'll be like, oh my God, what has happened? Or ask your classmates. So how do we go from microcanonical partition function to thermodynamics? What's our state function? Go ahead.
So this particles are indistinguishable, right?
If it was indistinguishable, I could not have written something like this. They're distinguishable. If it was indistinguishable, I could not say particle number 1, particle number 2. I could not say Kinjal asked me a question or Jared asked me a question. Jared is not here. I could not say Kinjal asked me a question or Sophia asked me a question, right? Because they are indistinguishable. Right now, I can say this. If they were indistinguishable, I would have, we will get to that later. And that's what happens when you're looking at quantum particles, because quantum particles are indistinguishable, and that creates problems. Yeah, so good point. Yeah, please interrupt me anytime there is a question. So our way of going from microcanonical to thermodynamics is through which state function? No, come on. omega NVE is your hint. Entropy, right? Is the S is equal to KB ln, in this case, omega of NE, right? There is no volume. So we have equation number 1. We can take its log and get our entropy. And from that, we should be able to manipulate it and get everything of thermodynamic interest. So let's start doing that. So what I would really like to calculate is not the entropy, but something one step further. I would really like to calculate temperature. And what is temperature? Temperature is partial S by partial E at constant NV, right? That's 1 over T. Therefore, the inverse temperature that we introduced, beta, is equal to partial ln omega by partial E at constant N, right? We showed this when we talked about microcanonical ensemble, and your midterm is basically going to be manipulations like this, a lot of these. So we have to use equation 2 in equation 1. So let's proceed. Let's first, so notice that we are not differentiating omega, we are differentiating log of omega, right? So let's take the log of the right side. So equation 1, log on both sides. What's that going to be? So ln omega is equal to ln n factorial minus ln m factorial minus ln n minus m factorial. Now, differentiating this with respect to m is really, really terrible and painful. We have to make some approximations. We have to approximate that capital N is much more than m. We are working in thermodynamic limit, and we are going to think about small m. Our energy is in the limit of not very, very large values, okay? Even though we will look at the results for all possible values of m, but in order to derive, that's what we are going to do. Furthermore, we are going to assume that this m itself is also much more than 1, okay? So this is the approximation we are going to make. If we make this approximation, then equation 3 becomes, we can use Stirling's formula, right? We can write ln n factorial as n ln n. Actually, we don't need to, you will see in a moment that we don't need to approximate this one. Why don't we need to approximate this one? Can anyone see? Because we are going to differentiate with respect to E, right? And E does not depend on N, E depends on M. So this thing does not depend on M. So it is what it is, we don't care. What we really have to approximate is these two things which depend on M. So this one becomes M ln M plus ln M, this thing, while this one becomes n minus M ln n minus M plus ln n minus M. Okay, so we have used ln k factorial is approximately k ln k minus k, as k is much larger than 1, right? That's our Stirling formula that we have used. Okay. At this point, we can approximate further by using this thing that m is much more than 1. If m is much more than 1, then ln omega becomes approximately ln n factorial. That term stays. M ln m stays.
Professor Tiwari,
Oh,
are you sure about your Stirling approximation?
what?
Are you sure about your Stirling approximation?
Yeah.
Because wouldn't it be minus m ln m plus m?
You're saying this is a plus sign?
No, I mean the second term should be m, not log m.
Yeah, but we are going to ignore it. So that's why I was happy.
Yeah.
That simplifies my life. because this m and m now cancel out. Thanks, Alex. So good. Alex made the guy on the Zoom is good. We don't even have to assume that m is much more than 1. We can just stay this way, okay? Because the m and m cancel out, right? We are just left with n. Good, thanks, Alex. So we are left with ln n factorial. I need to drink coffee. Minus m ln m minus n minus m ln n minus m plus n. Okay, is that clear? I know it looks like lots of plus, minus, cancel, 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 but if you go through it, do it yourself once. It's really not that complicated. Okay, you have to do it once yourself. So let's call this equation number 4. So let's try to look at big picture. What are we trying to do? We want to calculate in equation number 2. We want to calculate the log of omega, the log of the number of microstates, and differentiate it with respect to the energy to get our inverse temperature beta, right? And we want to differentiate at constant n. If you are going to differentiate at constant n, is this going to matter? No, that depends only on n. Is this going to matter? No, that also depends only on n, right? So we are left with a relatively simpler expression that we can differentiate. So let me write that down on the next page. So I will repeat that expression. So we have equation 4 that ln omega is approximately ln n factorial plus n. These two things do not depend on energy or on m, so we will lump them together, minus m ln m minus n minus m ln n minus m. Okay, and what do we seek? Equation 2 said beta is equal to partial ln omega by partial e at constant n. Equation 4 does not have any e, it has m, right? So we have to do just a little bit more algebra. We have to remember that e is equal to m times epsilon, right? The number of states that you have in excited state multiplied by number of particles in excited state multiplied by 1 multiplied by epsilon is e. So this thing is partial ln omega by partial m epsilon at constant n. Epsilon is a constant, right? We just defined what is the value of the excited state. In this problem, epsilon is a constant. So 1 by epsilon, partial ln omega by partial m at constant n. Okay, so let's call this equation number 5. This is why we want to differentiate ln omega with respect to small m at constant n. So let's do that. So let's go to equation 4 and differentiate it. So equation 4, which is this one, says partial ln omega by partial m. What is partial m of this? 0. What is partial m of this? 0, right? Those two things do not depend on m. The third one depends on m. So let's do that. So what do we need to do? We need to do partial by partial with respect to m of minus n minus m ln n minus m minus m ln m. Okay, that's what we need to differentiate. It looks terrible, but it's actually not that bad. You have to be careful with the minus signs in this one. Let's do it. So we have to differentiate both these sums one by one, right? And for each sum, we have to use product rule. So I will just write it down. And again, I suggest that you do it carefully at home and do it yourself. It's trivial, but it's easy to make a mistake. So this is going to be minus n minus m, and then you differentiate this term. So that gives you a 1 by n minus m multiplied by a minus sign because it has minus sign, right? That's the first one, followed by keeping this one constant. So ln n minus m multiplied by, again, minus 1. The m ln m term is easier. That gives us m multiplied by 1 by m minus ln m. That's the derivative, okay? Let's pull it all together. What are we going to get? How much is this thing? This first thing is -1 multiplied by -1. How much is that? +1, right? So this is +1 plus ln n minus m. This is -1 minus ln m. So what do we get? We get ln of n minus m by m. So partial ln omega by partial m is equal to ln of n minus m by m. Or partial ln omega by partial m is equal to ln n by m minus 1. Let's call it equation number 6. So now we have to focus on equation 5 and equation 6, and that allows us to get the temperature out of this approach. Equation 5 says inverse temperature is nothing but this partial the derivative in equation 6. So if you look over here, this is exactly the partial derivative that we needed here, right? That's exactly what we needed. So we have that quantity. So on next page, put equation 6 in equation 5. So what do we get out of that? We get beta is equal to 1 by epsilon partial ln omega by partial m at constant n. And that becomes beta is equal to 1 by epsilon ln of n by m minus 1. That's equation 7. So all of a sudden now, ensembles, microcanonical, canonical, everything has disappeared. We have a relation that connects the inverse temperature with the energy scale and with the number of spins that are in the excited state. Okay, so let's see if this equation makes sense, especially if it agrees with our intuitive picture. So this means beta epsilon is equal to ln n by m minus 1, or n by m minus 1 is e to the power beta epsilon, or 1 plus e to the power beta epsilon is equal to n by m, or m by n is equal to 1 by 1 plus e to the power beta epsilon. Okay, this is a lot of math. Physically, why should we care about the number m by n? Does that number have a physical picture? What do you think, Nick? Fraction. Is the fraction of states in fraction of particles in the excited state, right? Yeah, it is probability if you think about it. So, right, if you have something like this, then you would say that m by n is equal to 2 divided by 6, right? 2 are in excited state, 4 are in ground state, they are total. So 6. So this is m by n. We cannot really talk about 6 because we assume n is much more, right, than 1. So we cannot really talk about n being 6, but that's the idea over here. So we're almost there in comparing this with our intuitive picture. Now we can go back and say that energy is equal to m epsilon, okay? I will delete this one because it will confuse later. So m by n is fraction of particles in excited state. So E is equal to m epsilon. Therefore, E is equal to epsilon multiplied by m. And what is m? M is n multiplied by 1 over 1 plus e to the power beta epsilon, right? Therefore, E is equal to n epsilon by 1 plus e to the power beta epsilon. This is the energy. It's not the average energy. Why is it not the average energy? Because we used a microcanonical ensemble, right? There is no fluctuation. Microcanonical ensemble is like, nope, this is the energy. You cannot deviate from it by any tiny value. This is the energy that you want to have. In canonical ensemble, which we will do next, you will see that there is an average value of the energy. Of course, as n goes to infinity, they two become the same. As we know, ensembles converge. Okay, so help me now to prove why this agrees with our intuitive picture. As t tends to 0, what happens to beta? Goes to infinity. So what happens to E in equation 9? No, the denominator goes to infinity. So E goes to 0, which is what we expected, right? As t goes to infinity, beta goes to 0. What happens to E? What happens to the denominator as beta goes to 0? This thing goes to 1, right? As beta goes to 0. So therefore, the denominator goes to 2. And therefore, the whole thing goes to n epsilon by 2, which is what we expected from the intuitive picture. So it's a very, very complicated way of doing the thing, but it's important that you go through this because this is, anytime you do a microcanonical ensemble, effectively, this is the picture you follow. You calculate omega and you differentiate it to get everything of interest. Go ahead.
So there is no temperature where like m equals to n.
Why not? You can solve it. Let's try to solve it. I'm going into dangerous territories. I can draw your face. You have a beard. So I'll remember. You have glasses. And you're smiling. That could be me. I guess you have hair also. Okay, so let's look at equation 8. Equation 8 says m by n is equal to 1 by 1 plus e to the power beta epsilon. What's the question you ask? Can we have m is equal to n? Can everything be excited? And the reason you probably asked this is because it looks like at high temperature, it's half, right? So let's do our thought experiment. If m is equal to n, what does it mean for the left side? It becomes 1, right? 1 is equal to 1 plus e to the power beta epsilon. Or 1 plus e to the power beta epsilon is equal to 1. Or e to the power beta epsilon is equal to 0. What does this mean? Yeah, it won't happen in the microcanonical picture. So you can see there is a problem. And why did this happen? Because microcanonical does not allow the energy to fluctuate, right? In canonical, you will see, yes, it can happen. It's just a low probability event, right? Microcanonical says, nope, energy has to stay constant, right? That's the problem. In canonical, let's get back to this and you will see there is a fluctuation possible. In canonical, just to give you a teaser for what's going to happen, the answer is going to look the same. The only thing that will happen is we will have average over here. Once we have average, sure, it can go wherever you want. Very good point. So which is kind of strange, but that's what it is. Okay. As a practice problem, just because in the exam and in homeworks, I will always have you derive things and try to plot them, as you saw in this homework, right? I will expect you to sketch things and try to make sense, which is in general good habit as you become scientists, right? Always sketch things and try to see whether it makes sense or not, right? It gives you quick intuition. So I would like you to sketch equation 9 for all beta. Equation 9 is going to show up in a similar form later when we do Fermi-Dirac and Bose-Einstein statistics. One of them, it's going to show up. I keep forgetting which one. So plot it, it's going to show up later, okay? And try to get a sense of how it looks like. Any questions? Okay. So the second, so we did the first approach. We solved this problem using microcanonical ensemble. Now we are going to solve it using canonical ensemble. Canonical ensemble. Even though the microcanonical ensemble told us things that make intuitive sense, you already saw a problem, right? You would surely there should be a configuration where everything is in upstate and it says it's not going to happen, right? There is a problem. So canonical ensemble, our interest is going to be to calculate Q of NVT, right? not omega of NVE, but Q of NVT. This is our canonical partition function. Once we calculate Q of NVT, how will we connect it to thermodynamics? Go ahead. A, right? A is equal to minus 1 over beta ln Q of NVT. So this is our game plan. Once we have A, then we can differentiate A with respect to temperature to get our average energy, right? So let's try to calculate Q. I'm going to go to the next page and try to write a bit smaller. Next operation is again going to be a bit of math, very different type of math. And it will show up again. So this is an important problem because the ideas that we do here keep showing up again and again. So we want to calculate Q of NVT. How should we proceed? Well, anytime you're stuck, which will happen many, many times, that's how things are. You should write down the definition of that thing, right? What is the definition of Q? Go to every microstate, calculate e to the power minus beta E nu in that microstate and sum it up, right? This is a reason why many of you will be tempted to use canonical ensemble as a default for many problems, because canonical ensemble, it's easy to write down what's going on. Microcanonical, what is omega of NVE? It's kind of abstract, right? It's number of microstates, and you have to go think about how you calculate number of microstates. This is actually quite easy. Think if you're doing quantum mechanics, you already have your energy states, right? So you can go and just calculate it. So, but watch out, because just because it's easy to write down does not mean for all problems, your life will be easier when you start from here. Okay, some problems microcanonical is a better way. And this is where you have to develop intuition. But to get started, canonical is way easy. You can just write down something and then start to like, really grapple with it and make your way. So, well, then the problem comes, how do we talk about E nu? What is the energy of a microstate, right? That's what we need to think about. So our microstate was given as something like 0, 0, 1, 1, 1, 1, 0, 0, 0, dot, 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 1, right? This is how we denote it, for example, a microstate. So we need to be a bit careful in writing down the energy of the microstate here. And we can say that the energy of the microstate is going to be given by, let's go to each of the particle. We have n particles, right? And they go from 1 to capital N. And for each particle, look at this binary number, okay? Whether it's 0 or 1, call it Nj, okay? So this is jth particle, and multiply it by epsilon. And that is the total energy. Does that make sense? It's a compact way, but if you look at it, stare at it, it makes a lot of sense. It's a nice way of writing it, right? So in this case, what I wrote over here, what would it be? It will be N1 is equal to 0. So N1 multiplied by epsilon is equal to 0, right? N2 is equal to 0. So N2 multiplied by epsilon is equal to 0. N3 is equal to 1. So N3 multiplied by epsilon is equal to epsilon, right? That's what we are summing. So it's a compact way of writing down what's going on. So we call, let's number our equation, sorry, 1 second. So let's call this partition function equation as equation 10. And let's call this E nu equation as equation 11, okay? So Nj has a name. It will become important later. It is known as the occupation number. Actually, I don't want to talk about occupation number right now. Let's skip that. So we are going to particle number J and seeing Nj is equal to 0 if J is in ground state, and J is equal to 1 if particle J is in excited state, right? That's the idea. And we can multiply it all together, okay? And multiply it and then sum it all. That gives our total energy. Cool. Now begins the math. Use equation 11 in equation 10. What does that mean? Equation 10 says Q of NVT is equal to summation nu e to the power minus beta E nu. And now I have the value of my nu. So it's going to look so horrible because I have a sum of exponential, and inside the exponential's power, I'm going to put a sum. It's like terrible, right? I'm a bad human. But you'll see why it simplifies very nicely. So this is e to the power minus beta summation j is equal to 1 to n nj epsilon. It's like if summations are integral, so it's like integral of exponential to the power integral, right? That's what we have done here. But you will see how in the moment it will magically filter out, but become really, really nice. And let's take a moment to understand what nu really means here. Nu means that we are looking at every n, right? N1, N2, N3, and that can be 0 or 1. N2 can be 0 or 1. N3 can be 0 or 1, dot, dot, dot. That's what we are doing, right? So here's the question. How many microstates does this system have? Sophia, what do you think? I overheard you were awake till 4 a.m. So it's okay if you give a wrong answer, but
There's two.
it's something related to 2, right direction. So there are n particles, right? And each particle can exist in 2 states.
Then zero. Well, because it can be 0, 1.
Yeah.
two.
So let's think about if there were total 2 particles, right? If there were total 2 particles, then let's write down the microstates. It will be 0, 0, 0, 1, 1, 0, 1, 1, right? If it was 3 particles, it would be 0, 0, 0, 0, 0, 1. What's the best way to enumerate all 3? I've forgotten my binary numbers. 0, 1, 0, 1, 0, 0, right? 0, 1, 1, 1, 0, 1, 1, 1, 0, 2, 3, 4, 5, 6, 7, 1, 1, 1. You see what's happening here? So how many states do we have here? 4. How many states do we have here? 8. So this is 2 to the power 2. This is 2 to the power 3, right? Because every particle is independent. So we will have total 2 to the power n microstates, right? If they were not independent, that would not be the case, right? So it's not 2n, it's 2 to the power n. So it's a huge summation. So let's write it down in more detail. So this is going to be Q summation. Instead of nu now, I'm going to write down n1 is equal to 0, 1, n2 is equal to 0, 1, and 3 is equal to 0, 1, dot, 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 okay? And it will become clear in a moment why I'm really explicit about everything. E to the power minus beta, and let's explicitly write down this sum. What is this sum? This is n1 epsilon plus n2 epsilon plus n3 epsilon plus dot, 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 okay? What is this now? We will keep the summation that we had over here. This is n1 is equal to 0, 1, n2 is equal to 0, 1, dot, dot, dot. Now something happens. This e to the power sum can be written as product of exponentials, right? Why? Because e to the power x plus y is equal to e to the power x multiplied by e to the power y, right? So we can write this thing down as e to the power minus beta n1 epsilon, e to the power minus beta n2 epsilon, e to the power minus beta n3 epsilon, dot, 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 right? All I have used here is that e to the power x plus y plus z is equal to e to the power x multiplied by e to the power y multiplied by e to the power z. When would such a approximation break down? Exponential of things is equal to product of exponentials. Would it ever break down? Never? Something simpler. Well, kind of simpler. It starts with a Q. If you're doing quantum mechanics and X was not a real number and X was an operator, this would break down, okay? Because quantum mechanical operators do not commute necessarily. So e to the power x plus y is not equal to e to the power x multiplied by e to the power y. You have to use something known as a Trotter formula and Baker, yeah, and it becomes actually quite complicated. But we are doing classical, and even in quantum mechanics, if x and y are numbers, nothing can stop us, right? So it's the problem happens when x and y are operators that do not commute with each other. Thankfully, we are not worrying about that right now. But if you do quantum field theory and things like that, then you will see these things matter frequently. And this type of ideas basically go up there also. The only difference is that you are dealing with complicated operators, but for now it's simple. Okay, so we have this. Now notice something else. Does anyone notice a simplification we can carry out now? We have this complicated sum which depends on all these many different variables at the same time. However, N1 comes up only through here. N2 comes up only through here. N3 comes up only through here. So we can take this very complicated sum and make it simpler. What we are doing here is, so let's write down this very complicated sum. So what does this very complicated sum mean? It actually means that you are going N1 is equal to 0 to 1 multiplied by N2 going to 0 to 1 multiplied by N3 going to 0 to 1 dot 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 N capital N going to 0 to 1 whole thing and the sum is taken over this quantity. This is the quantity that is being summed. E to the power minus beta N1 epsilon, e to the power minus beta N2 epsilon, e to the power minus beta N capital N epsilon. Okay. Now I can make a mega assumption, mega approximation. It's not assumption. In this case, it is not approximation, it's mega clarification. This quantity can go up here, right? It has no dependence on N2. This quantity can go up here. This quantity can go up here, right? They don't depend. It's if you had something which was looked like N1 multiplied by N2 epsilon, then you're screwed. You cannot do this, right? But since it is so separate, let me write down this big formula on the next page, and then I will start from there. So if you have not copied it, don't worry, I'm writing it down again. So I want to write it down in a bit more compact manner, okay? So what did I say? I said Q of NVT is equal to summation over nu e to the power minus beta e nu. And then I said, this is Q is equal to N1, N2, N3, dot, 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 and all of them belong either to 0 or to 1, e to the power minus beta summation j is equal to 1 to n epsilon nj, right? This is what we wrote on the last page. And then we use that e to the power x plus y plus z is equal to e to the power x, e to the power y, e to the power z. In other words, e to the power summation x can be written as product of e to the power x. Take note of this equation, okay? This one seems very simple, right? Oh, yeah, of course, exponential of sum is equal to product exponential. If I just threw this one at you, you'll be like, wait, what happened? Where did the pi come from? Okay, but that's a notation we will use a lot of times because of its simplicity. So this equation can be written as, I'm not writing anything new related to what I did on the last page. This can be written as N1, N2, N3. All of them belong to 0, 1, product of from j to 1 to n e to the power minus beta epsilon nj. Okay, this is exactly same as last page. There is nothing new over here, just a bit more fancy notation. And then this thing becomes, now I will write down the equation on the last line. This thing becomes N1 is equal to 0 to 1, N2 is equal to 0 to 1, and N is equal to 0 to 1, e to the power minus beta epsilon N1, e to the power minus beta epsilon N2, e to the power minus beta epsilon small n capital N. And the key physical picture here now, or at this point, mathematical picture, is that this quantity can be brought outside all the other summations because they do not depend, it does not depend on N2, right? So you can bring it outside. This quantity can be brought over here, so on and so forth, right? So this summation becomes N1 is equal to 0 to 1 e to the power minus beta epsilon N1 multiplied by summation N2 is equal to 0 to 1 e to the power minus beta epsilon N2 dot dot dot. This is drastically simpler because instead of a complicated multi-dimensional sum, you have a product of one-dimensional sums, right? What else is simpler about this expression? Can we calculate this sum? It goes over two values, right? It's really, really easy. Is this one different from this one? Why, Michaela?
I mean, this is.
It's only the variable that have been changed. It's like saying integral sine x dx, is it different from integral sine y dy? No, it's the same thing. You have just replaced x with y. They are the same integral. You have n copies of the same integral. You have n1 is equal to 0 to 1 e to the power minus beta epsilon n1 or n2 or n3, whatever you want to call it, whole thing to the power capital N, which is awesome. So all that complicated stuff actually simplifies so much. The reason it's simplified because the particles are independent. In life, things are not independent, right? This won't work for most things, but this is already powerful and we can develop theories. We will develop theories that introduce perturbations from this model. And now this sum itself is very easy. This is, let's put n1 is equal to 0. If n1 is equal to 0, what is the value of this thing? 1, right? E to the power 0. And if n1 is equal to 1, what is the value of this thing? E to the power minus beta epsilon to the power n. So we just got our Q of NVT. Q of NVT is equal to 1 plus e to the power minus beta epsilon to the power n.
If the particles are indistinguishable, you wouldn't be able to split that sum and product thing that you've done, right? With all
No, I will tell you the approximation just in a moment. Yeah, this worked only because of the distinguishability. I will come to indistinguishability just in a moment. Okay. So before I calculate thermodynamics from this equation, I want to go to our approach 3 and show how I could have written this equation in one line instead of going through all this math. Wait just a moment. Okay. So we have just shown that Q of NVT is equal to, and T, and it's strictly speaking Q of NV beta, but we know what is the relation between beta and T, so we don't worry about it that much. Q of NVT is equal to 1 plus e to the power minus beta epsilon to the power n. And in order to do this, I had to drag you through 2 pages of algebra talking about quantum mechanical operators, which didn't really matter here, but all this. Could I have written down this equation in a simpler way? How? This is, so think, yeah, exactly. So think approach 3. Only one particle. Let's say, don't worry about n particles. We just think about only one particle. If there is only one particle and I want to write down my canonical partition function for this one, e to the power minus beta e nu for this particle, well, that's going to be simple, right? This one particle has only 2 microstates. The reason happened is the reason this all became complicated and we were counting this with Sophia is because 2 particles, you have 4 states, 3 particles, you have 8 states, it explodes. 1 particle, you have only 2 states. The ground state is E nu is equal to 0. The excited state is E nu is equal to 1. So one particle partition function is 1 plus e to the power minus beta epsilon. And we know very well that, and this is what actually Omar was asking on the Slack, we know that Helmholtz free energy, A, is extensive, right? And this is why it's also so nice to take StatMech after 684. Otherwise, this becomes some abstracting, but it's actually very simple. A is extensive, right? If you have in the thermodynamic limit, as you start, and this is why this I will call this an approximate approach, but it's got the right idea. A is extensive. So if you take a system and take another system and you put it both together, their Helmholtz free energies are going to sum up, right? So A of N1 VT plus A of N2 VT is going to look something like A of N1 plus N2 VT, right? That's the idea behind extensive quantities. And what is the connection between A and Q? A is equal to minus 1 over beta log of Q and VT, right? So this means that Q of N1 plus N2 VT is going to be Q of N1 VT multiplied by Q of N2 VT, right? This is why we call it partition functions. For independent particles, the partition function is a product of individual partition functions. For independent system, net partition function is a product of individual partition functions. And why product? Because in thermodynamics, things are sum. And thermodynamics is connected to StatMech through a log, right? It's simple yet profound. The log shows up again and again and again. So this means if I have calculated Q1, the one particle, let me write down a 1 over here, okay? Q1, the one particle partition function is 1 plus e to the power minus beta epsilon, then the n particle partition function is simply going to be Q1 to the power n, because they are distinguishable, they are independent. So we can just take and multiply it and take power to the n, and we get the same answer, right? So we could have derived this answer through this intuitive approach also. Now the question Vedant asked on Zoom is, what if the particles were indistinguishable? How would we correct this Q? What should we do? And one moment. So I'm going to come back to getting thermodynamics out of this, but I want to have this discussion before I get to that. So what would I do if the particles were indistinguishable? Any ideas?
You just account for the fact that you're like, so if you counting extra number of times, so you divide by the number of times you're counting additionally. Like if you just
Tell me, what is that?
So I think n factorial, I guess, would be it.
Okay, so I'm not saying whether you're correct or wrong. So Vedant says Qn indistinguishable should be Qn distinguishable divided by n factorial. Does everyone agree with this?
Yes.
He agrees, Nathan agrees with it. Is there anyone who disagrees with it? Go ahead.
Yeah, because so this can happen only when all the n particles are in different microstates. So
yeah, so I'm going to write this down as think. And with a 65% probability, I'm going to give you a problem on the midterm about this one. So please think. What does 65 mean? I don't know. More likely than not, let's put it that way. This turns out to be correct in the very large n limit and under certain approximations. Either in the next midterm or in the next homework or somewhere, I will give you a problem where you will calculate things in a few different ways and see why this can create problems, especially when n is small or the number of possible microstates is small, okay? So this works in some cases, okay? And think about it. It's actually, no, I won't call it 65. Let's make it actually 40% probability of showing up on midterm. So,
Do you have,
huh?
do you have to divide it by the number of partitions?
Well, you will see, you will see, you will see. Okay, but hopefully the point I made here so far is we did it through microcanonical, right? Which was explicitly the number of combinations. Then we went, but that had a problem. The energy was fixed. Then we went to canonical. We calculated our canonical partition function explicitly. We calculated the value of E nu, and we got an expression. And then we realized this expression is nothing but a product of the individual partition functions. And that led us to approach 3. We said, well, we could have just written it down for independent particle that are distinguishable from each other. This is correct. Okay, what we haven't shown yet, and I raised to you the question of truly indistinguishable particles. Okay, you should start thinking about it because it will matter a lot once we get to Fermi, Dirac, and Bose-Einstein. But for now, what I want to do is to take this expression for Q, which I derived from approach 2 or approach 3, and get some thermodynamics out of it. So that equation is, what is the number for it? I don't know, which number did I stop at? 11, 12, looks like 13. Doesn't matter. So this is equation 13, okay? So let's focus on equation 13. Equation 13 says Q is equal to 1 plus e to the power minus beta epsilon to the power n. Okay, so we can write down our Helmholtz free energy automatically. Minus beta A is equal to ln Q, right? That was the definition of, that was the relation between, we proved this, right? Remember? And the proof was not exactly trivial. We calculated average energy, then we calculated average entropy, and we used that the canonical approaches the macrocanonical in the very large limit, right? It's worth remembering that in our approach, this relation, this derivation was not exactly trivial. We had to work through some ideas. But now that we have this, we can write down minus beta A is equal to n ln 1 plus e to the power minus beta epsilon. This is equation number 14. And we can calculate average energy. Does anyone remember the expression for average energy from canonical partition function? It's a derivative. Minus, you have used, you should, basically it should start getting engraved in your heads now because you have used it in homework and you will keep using it again and again. So we just have to take this thing, its log, and differentiate it with respect to beta, right? It's not a complicated operation. When you do it, you will see that you get exactly the same answer that you had before for microcanonical, okay? Just one line of algebra. But something is very different. Microcanonical, we did not have this Dirac bracket hanging. Now we have average. So the question you asked, can everything be in excited state? That can happen here, right? Because you can now go and calculate the fluctuation in this example. I'm not doing that here, but you can do it, right? And you'll see that it's actually possible. You can talk about the probability of a state with energy. You can actually talk about probability of E is equal to n epsilon, right? You can do that over here. This is also a good practice problem. Just calculate that probability and see how much it is. In microcanonical, that probability was 0, right? Unless E had a particular value, right? Microcanonical is very restricted, right? So that's how it works. Any questions? Okay, I'm going to stop here. I don't want to start grand canonical over here. So we did canonical. In Chandler, grand canonical is quarter of a paragraph. And he just says, do it. It's the same idea. It is trivial, no, but we will take more time doing into it. All of what I did today is covered on midterm, okay? Tuesday's class is not going to be on the midterm. And some people came late. So I want to remind that midterm will be released Thursday morning, which is 2nd of March, apparently. Ethan told me, right? So, yeah. Okay, blame it. What I believe is Thursday morning. So Thursday morning, it will be released. No class on Thursday. We do have class on Tuesday. Thursday morning, early morning, like 6 a.m., 7 a.m., I will release it. And then it will be due Tuesday morning. And it will have a bunch of problems. It will take a bunch of time. I don't know. It will be type 2 fun. I mean, what can I say? It will have bonus problems. Please try to do the bonus problems. Okay. And, it won't cover Grand Canonical Ensemble. It will cover everything that we did over today. I will have your graded second homework and your graded first homework in class on Tuesday. I will try to, I will bring it graded so you can look at it. And I will also release some answer keys by Tuesday, so you can look at all that before the midterm starts.